Okay, in our last video, we did some physical calculations. Based on what was in our image, we determined temperatures and we determined densities. And just as a recap, the final thing we calculated was the exterior density, the density of the gas in the surrounding cloud out of which these stars formed. And here you can see my students' results from this semester. And these densities, these exterior, external, outside densities, typically 100 to about 10,000, some a little less, some a little more, but most are in that range. And that's great because those are the typical densities for clouds out there in space, in the galaxy. That's a great check. Now, the other thing we calculated on the way was the density on the inside of the star forming region. Stars have formed, they're spitting out ionizing photons, it ionized and heated the gas, and then this gas expands until it establishes pressure balance with the outside gas. And since it expands, the density goes down, and they measured densities on the inside, here it is, kind of in the range of 10-ish to 1,000, about a factor of 10 less, and in some lower, and some higher, but in that range, lower densities than on the outside. And that makes sense because the inside has been expanding because it's hot. But these densities are still pretty high compared to empty interstellar space. Averaged over the galaxy, the typical density is about zero point 0.1 particles per cubic centimeter. And so on the inside, we're getting 10 to 1,000. The outside, we're getting 100 to 10,000. So it's still dense in there in that hot central region. So it's dense and it's ionized. Again, we saw narrowband for almost all of these. We see narrowband. That means the gas in there is hot enough to be ionized. And this is a recipe. Gas that is dense and ionized, it creates radio emission. This is our third continuum emission mechanism. Back in modules 1B and C, we had an introduction to thermal emission. That's a continuum emission mechanism. We had an introduction to synchrotron emission tied to magnetic fields. And that's another continuum emission mechanism. The third one completes the set is this one. It's called bremsstrahlung, and it's caused by dense, hot, ionized gas. Now, we'll learn a lot more about all three of these continuum emission mechanisms in Module 4. These have just been little introductions, and this is just a quick introduction to bremsstrahlung, or braking radiation. So if it's hot and ionized, the protons and electrons separate. It's mostly hydrogen. So you separate the electrons from the nucleus, and you have just protons and electrons floating about, and they encounter each other. And when they do, the electron will get deflected going around the more massive proton. Deflected and decelerated. And when it decelerates, it emits a little bit of energy. You can see it here, and it comes out in radio waves. Now, if it's low density, there won't be enough of this, but if it's a dense region, it all adds together and it can be a pretty strong signature. So, as a check for our density measurements and our temperature conclusions, let's just see if our star forming regions are emitting radio. And we've already taken the observations in an earlier video, so we're going to now process these and measure their brightnesses in Janskys. So let me see if my observations came back. This semester, I'm doing the monkey head. Here it is. And as my calibration source, I did the crab. I'm going to process these now. First, I'll just look at my preliminary data product. And indeed, yep, something there. That's great. And go back a page and just check with the crab. It, of course, should be there, just making sure there's nothing wrong with the observation. No, looks great. All good. Okay, so let's process these. I'm going to create a new cartographer job. Name it something if you want. If both channels look good, we press sum. We've done this before. I'm just going to review it rather quickly. Gain can be set to interpolated. It will use both the noise on, off at the beginning and the noise source on and off at the end. The coordinate system, I'm going to change this to equatorial. And that's kind of our standard system. We observed it in an equatorial raster, so we'll process it in an equatorial raster. That's right ascension declination. Time delay correction, we want that turned on. That will correct for the little zigzag effect we see here. And, as long as you're not doing this in class, you can turn those raw images on. You can see what it looks like before all of the radio cartographer algorithm works its magic. If you're doing this in class, you may want to turn it off. It'll go faster if everyone's doing it simultaneously. This doubles the time. And then frequencies to eliminate. So again, looking at the spectrum here, this is really clean. Sometimes there's interference at 1381, sometimes at 1400, and here's hydrogen out here at 1420. I've already cut all those out, even though I don't see it in mine. Just in case you see it in yours, this is how you cut out 1381. You add a skip frequency between 1380 and 1382. If you have a little blip around 1400, cut from 1399 to 1401. And this time we're going to cut out the hydrogen line because we're going to map this source and we just want to convince ourselves that it's not 21 centimeter line emission, but it actually is Bremsstrahlung. So let's cut out the hydrogen emission line 1419 to 1421. Otherwise, subtraction scale 6 beam widths. That's good for small sources. And this is faint. So most of your star forming regions, they're probably going to be faint unless you're imaging like the Orion Nebula, Orion A, in which case, if it's Orion that you're doing, bright target with airy rings, but anything else, any other star forming region, you can set that to faint target and it will set the rest by default. Get this running. Okay, it's pending. While it's doing that, I'll go process my other one, my calibration source. I used the crab. So I'm creating the new cartographer job. Same deal, sum, interpolated, equatorial, auto, raw is on. There are my skip frequencies. The only difference is it's a bright target. Now the crab is bright, our calibration sources are bright, so we'll use these settings for it. Press the let's go. Come back over to Monkey Head, and it's done, so I download it. And let's go back here, radio, crab. Is it done? It's done, so I'm going to download it. Okay. Now that we've processed them in Skynet using the radio cartographer algorithm, we're going to open them up in Afterglow. We've done this before. You just go to Open Files. You go to your workspace, Upload, and there they are. I can upload them, but I've already done this, so I don't need to upload them again. Then you click on them and open them, and here they are. Here's my image of the monkey head. And remember, you have many different layers. Here's the raw layer. before we did all of our background subtraction, RFI removal, etc. It's the main layer that you want, the first one. Okay. And let's check out the crab. Looks good. Here I've adjusted the stretch mode to square root and hit bright target so I can see the airy rings, but that's arbitrary. This being fainter, you may have to play with the stretch mode and the levels to bring it out a little bit, but I can see it. It should be at the center of your image. Remember, your optical image is about the size of my cursor. This is a 4-degree field. This is much bigger. All the optical actions right at the center. So that's not it. That's something else, something even brighter. But this is my target, the monkey head. Okay. So we're going to photometer both of these. Just to remind you how to do that. In radio, first you have to go to settings and photometry. And it's probably going to be an optical. And so for radio, I really need to add a button for this, but until then, you got to do it manually. Centroiding radius, we change that to 28. So you can click within 28 pixels of the center, and it will centroid it for you. The aperture is 28. The inner annulus is 50, and the outer annulus is 70. Just show you what that looks like. Should look like this, with your airy ring between the aperture and the annulus. So I come back out to the workbench, come over here to source catalog, make sure include sources from other files is turned off. Then go to photometry. Looks like I've already clicked on it from before and put down my aperture and my annulus. And it says the flux is 425. And again, that's not in a meaningful unit, that's noise source units. Remember, at the beginning and the end of every raster map, we turn on a little radio noisemaker up in the receiver. This is now calibrated to that. 425. Remember that. The crab, we got 17,601. Okay. So going back to this spreadsheet, on sheet 3, I have a little calculator, same calculator we had in 1B and 1C. And what was it, 425 for the star forming region? And, oh, I forgot already, so I'm just going to double check. 17,601, 425, 17,601. Okay, so that's the brightness of each in noise source units. So we just follow the equations here. First, we want to know the brightness of the star forming region in calibration units. What fraction is it of the calibration source? And that's just orange divided by yellow. It's only 2%, 2.4%. Okay. Then what's the brightness of the calibration source? That's what makes it a calibration source. It has a known brightness in Janskys. And for this, we go to our Astromancer tool, source calibrator. I used the crab, that's Taurus A. Make sure you pick the right one, very important. And then you can upload the file, crab, and that will make sure you have the right frequency range, and the date of the observation matters for some of these, not for others. And then you come over here and read the flux density, not the effective frequency, just the flux density, 486.6. That here, sorry, I didn't say that right. 846.6. That's 847 Janskys. And so the brightness of my star forming region is its brightness relative to the crab times the brightness of the crab. So about 20 Janskys. So this star forming region, not the brightest thing, but not the faintest either. With the 20 meter, we can get down to a few tenths, maybe even a tenth of a Jansky at this wavelength. This is 20, so easily detected, and indeed that's what we saw. Okay, now for the rest of this video, I'm going to give some hints if you were not able to get a radio map. Right now, we only have one telescope. It's in the Northern Hemisphere. Some of you did Southern Hemisphere targets. So what can you do? Okay. Well, you can go to this page called the Skyview Virtual Observatory. Do it over here. Skyview Virtual Observatory. We'll use this a lot in later modules. It's a giant archive. Come here, you go down to the query page. Then you're going to look up your source. Let's see, let's do 30 Doradus. Oops. 30 Doradus. If you know the source name, you can type it in there. This is the Tarantula Nebula. This is a southern target. Can't see it with our radio telescope in the north. Our southern radio telescopes aren't ready yet. So what can you do? We can grab some archival data. I'm just going to show you how to do that. If it doesn't recognize the name, just go to Afterglow, your optical image. I don't have mine up at the moment, but find the center of your optical image and type in the coordinates here, like they suggest. Then you're going to come down and click on the GB6 catalog. It's at a different wavelength. There's one that's at our wavelength, 1420. That's pretty close to our wavelength, but it's also only the Northern Hemisphere. So it can't help us in the South. But this one, the GB6 catalog, it did get down to the Southern Hemisphere. It's North and South. It doesn't have every part of the sky. It's really old. It's messy, but it's something you can use in your blog if you weren't able to get something. Notice the frequency, 4850. Different frequency. We'll have to keep this in mind when calibrating. Okay. And then down here, let's grab like a 4-degree chunk of the sky. And we're not yet set up to do photometry on these images, but once we are, 1900 pixels will kind of match the same pixel scale as the radiocartographer images. Okay. For this telescope and this frequency. So I'm going to submit the request. There it is. So you see it. Control minus. It's ugly. But it's something. There's something there. And so we'll be able to measure this. Come down here. Download the FITS file. Okay. And then you can come back here and change your target to a calibration source, such as SIG-A. Submit the request. There it is, very bright. Come over here, download the FITS. Upload these into Afterglow, and then you can do the same analysis. Now, at the moment, we don't have the apertures working on these images, but that should be fixed within a day or so. So I'm just going to assume that works, in which case you can do the analysis the exact same way. In Afterglow, you'll put an aperture around your star-forming region. You'll put an aperture around your calibration source. And then when you go to measure the brightness of the calibration source, what was this one? I said use SIG-A. Just keep in mind that these are done at a different frequency, from 4,700 to 5,000 megahertz. And they were done like a long time ago. I'm just going to guess 1980. Well, the date doesn't matter with Cygnus. Cygnus doesn't change in brightness. Taurus does a little bit, but if you use Cygnus, it doesn't matter what date you put in here, but you do want to get the frequency range correct. And I guess the date doesn't run that low. I'll put 2002 back. Okay, it's happy now. And it gave me a flux density. It'd be much lower. At higher frequencies, often the sources are fainter in terms of Janskys. But at least you'll be able to measure something showing that there is a radio source there and measure a Jansky brightness for it, albeit at a different frequency than everyone else is doing. All right, that's it for this video.